Hello, ready for the next part of 1.7? What we already did was so-called direct proofs. And so I remind you what is a direct proof. So a direct proof, and when we talk about direct proofs, one always talks about implications. So if one of an implication like that is you assume P to show Q. Okay, that's the strategy. You assume P and then you find arguments that finally lead to Q. That's what we call a direct proof. Now we see there are two types of proof. There are other types of proofs, but these are the ones that we're going to discuss here. That is contraposition. That's a word that you have heard, and contradiction. That's a word you have heard, but not in this context of proving. So first of all, what is the proof of contraposition? And it is again about implications. And why? Because of course, what is contraposition is the fact that an implication is logically equivalent by taking the negations, by making the new hypothesis the negation of the conclusion, and the new conclusion the negation of the hypothesis, or the original hypothesis. So, and that we know that they're elementary equivalent, and one way that we know this is by, for instance, making the truth tables and verify that the truth table on the left hand side is exactly the column that you get is exactly the same column as the right hand side. And why is this useful in proving? Okay, so what we then do is a proof by contradiction. How does that work? Well, in some sense, it's the same as a direct proof, except that you now do the direct proof on this guy. So you assume not Q and to show not P. Now be very careful, right? It is, notice that we take negations, but you also switch the order of Q and P here. That's very important. For instance, if you would assume not P and you conclude not Q, that doesn't prove, well, you proved something, but you didn't prove the original implication. Okay? So it is this thing that we want to do. Now we might say, oh, that sounds silly. Why would you make things like complicated like that? Well, here's an example. So show that if 3n plus 2 is odd, then n is odd. Okay. Now you could try to do this. Okay, so the direct proof say assume that 3n plus 2 is odd, but then what are you going to do now? But the fact that 3n plus 2 is odd. Now remember, odd is the predicate. Odd n means that n is odd, but there is a formal way of saying that. There is an k such that n is 2k plus 1. It's an even number plus 1. An even number, twice a number is an even number, and then you add 1, you get an odd number. So that's the formal definition of our predicate. So formally what we're saying here is that odd 3n plus 2 implies odd n. Now, we don't need to unravel this time these predicates as unlike in what we did in rules of inference, because we're not going to do any other inferences. Rules of inference is where you have many predicates and you try to combine logically, make conclusions of them, but here we have basically the predicate odd. So what we're going to do is, so what is the direct proof, as I said, would say assume that 3n plus 2 is odd, but that would not help us much. So proof by contradiction. So I'm not going to use the predicate either anymore. So just to not get distracted, I'm going to erase it, this predicate. Because as I said, this is not what we're going to, that's not the focus. Let's focus on what is important here. So proof by contradiction means that, remember, so this would be what stands for P, and this would stand for Q, right? So this would be P and above and Q. So I have to assume not Q. So assume not Q. Well, let's not write down what that is, just to say what it is. Assume n is not odd. Now, of course, again, negative things are very hard, but we know very much what this means. I.e., this means n is even. Now, be very careful. We can do things with that, but what we need to show is, and that's why I always would suggest, especially when you do proofs by contraposition. Sorry, I said contradiction and I meant contraposition, because contradiction is still different. Contraposition. So sorry that I used the wrong term. And here I did it twice. So, in the proof by contraposition, apologize for saying it wrong and even writing it wrong, what we need to do is assume the negation of the conclusion, and then from that to derive that the negation is true, namely that 3n plus 2 is not odd, so meaning even. Now let's try. So I would challenge you, I mean, in the textbook they give a little bit of indication also to try to prove this in a bit so-called direct proof, starting from the assumption that 3n plus 2 is odd. Notice that's a totally different assumption than the one that we are now making. We are now actually not making an assumption about 3n plus 2, we are making an assumption about n. That is because n was that was the q was saying something about m. So assume n is not odd, so n is even, to show that 3n plus 2 is even. Now, what is this? How can I use this? Well, n is even, we know that means that n can be written as twice a number for some k. That is, if we don't write n in a way that we can do some calculations with, we are stuck. But we can do that here. We can write n as 2k. So, now remember what we are going for. That's always the case. Always highlight for yourself, what is this I'm going for? I am going for 3n plus 2. So now 3n plus 2. I can calculate it because I can plug in 2k there. 3 times 2k plus 2. And what I have to show is that this is an even number. How do you show that the number is even? By, if you can factor out a 2, and there's nothing left, of course. So, can I factor out a 2? Yes, because you can factor out 2, and then there's 3k left in the first term, and 1 in the second term. And so, this is some number. This is a number. It doesn't matter what it is, but it proves that 3n plus 2 is even. And that's exactly what we needed to prove. And remember, I put this little box in there. The textbook puts a triangle, which I have never seen anywhere else, so I don't know why they got that from. Okay, that is an example of a proof by contradiction. And here is another one that is even perhaps harder to do if you would want to do a direct proof. So if n is equal to ab, by the way, I didn't say it here, but everything are integers here, positive integers, natural numbers. In the previous case, actually, with negative number, but here we're dealing with positive integers. In the textbook, they make it very clear what it is. Then, so if what it says, if a product of two numbers is equal, a and b is equal to n, then either a is less than radical n or b is less than radical n. Kind of says that they can both not be big, because if they're both too big, then they won't multiply to n. So perhaps this is true, perhaps it's not true. It's not immediately clear, right? So again, this would be our p and this would be our q. So prove by contraposition. Sorry about that, but this time I say it right? Contraposition. What do we do? Well, assume that the hypothesis is false. So assume not a less than radical n or b less than radical n. Now I do this explicitly, I put a not in front of the whole thing, because remember, negations are not so easy to deal with. We have to be careful. We are negating here a conjunction, right? So perhaps to make that a little bit more clear, let me really write here a logical or. And now I know what to do. I know that I can do the Morgan law on this. So this means not a less than, okay, I'll write it, not a less than radical n, and not b less than n, radical n. And again, I should perhaps, if I'm making it so formal, let me use the formal notation for not, okay? So not this and not that. You might say, are you not now negating a predicate? Okay, this is subtlety, but it's perhaps something I should say one more time. When we talked about proofs, all the previous lecture, I told you that what we do is that this is actually a universal statement, right, for all n, a, and b. That's, again, there was no quantifier, so it was already a predicate, not a statement as it was written down. But the assumption was there is for all n, a, and b, a universal quantification. And then what we do is, when we prove this, we do the proof by universal generalization. Namely, we say, let n, a, and b be some particular numbers. So now they are no longer variables, but they are really numbers now. And therefore, a is less than radical n is a proposition that is either true or false. Okay, so, but it's just a subtlety. Don't pay attention. That's not so much, not important. It doesn't change the proof, but it is something perhaps that you might worry a little bit about. So, going back to what we have here, again, I want to unravel my knots as best as possible. And the best thing here is to say, well, if you're not less than or equal to, then you're bigger than. And b is bigger than n. So what I should do, as I said, always remind myself what I have to show. Perhaps I should have done that first, but let me do that. So what I have to show here, I have to show what? Not p. That means I have to show n is not equal to ab. Be careful. I don't want to show that n is equal to ab. In contraposition, what we need to do is prove the negation. Okay? Okay, so proof, so argument. Well, I have that a is bigger than radical n and b is bigger than radical n. These are all positive numbers, and it's a simple property of big numbers. If you multiply two numbers that are bigger than two other numbers, then their products are bigger. So, meaning ab is bigger than radical n times radical n. Okay, on the right-hand side, twice the same number, but this would even be true if on the right-hand side would be two other numbers too. In other words, we say that the order is preserved by products. That's for positive numbers, right? For negative numbers, it just flips over. But we are dealing with positive numbers here. That's also clear from the fact that we're taking positive radicals. Okay, so AB is bigger than radical n times radical n. Well, radical n times radical n, that's n, right? Oh, AB is bigger than n. Well, that implies in particular that it's not equal to n, and I'm already done. So you see, sometimes a proof by contradiction, once you have unraveled everything, it becomes very quick. I'm not saying always, but this is a case where we have this. Okay. Let's go to the other. Okay, we did this example, so let's go to the other time. Proofs by contradiction. Now that is a little bit harder. Now, it's not harder, it is weirder, let me put it that way. In fact, it's not harder because that's why mathematicians very often use proofs by contradiction. I mean, today I was working on my own stuff and I think I used at least 10 proofs by contradiction. I am now talking, so I will, what does that mean, proofs by contradiction? So contradiction, remember, let me first remind you that a contradiction is a statement P that is always false. Is that possible? Well, yeah. For instance, the statement R and not R. So examples. R and not R. That can never be true, because to be true, and to be true, both the left and the right have to be both true. But you cannot be at the same time true and false. Okay, that's so that's a typical example of a contradiction. And in fact, it is almost always that we will mean when we do a contradiction. So what is a proof by contradiction? How does it work? First of all, it's not only by implications. It can be about anything. Okay, and so what you try to prove is, so you're trying to prove a statement P. So to show P. So okay, let me say it this way. Okay, I'll give an example very quickly, but here it is. So we have a theorem, right? That's like This means like a nice fact about mathematical things that are not so obvious, and so it needs a proof. That's the theorem. And the theorem is P. I am just giving a name to whatever it is, P. Now, the proof by contradiction is, and this is very strange. In order to prove this, we're going to assume that it is not true, not P. So, and the idea is this. So, I'll give you an example, and hopefully it will become more clear, but I'm going to try to do this. Remember when we made truth tables, we said we have various rows, and each row represents a possibility where one predicate is true and the other is false, etc. Proposition is true or false, etc. I would call them a world, a scenario, if you think of a story, or a world like a universe, if you think about the meta-universe, if you're into that stuff. So what is the proof by contradiction try to do? In the same vein, the same reasoning, it says, okay, I'm claiming that in this world P is true. Now, how am I going to convince you? By making it clear that if P would not be true, then all hell would break loose. In other words, you get something silly, impossible. You get a contradiction. So it is, in other words, I'm going to show you that not P is impossible, and therefore, if not P is impossible, P must be it. So that's how a proof by contradiction works. So you assume not P. Now, what is the goal here? So goal, I kind of say goal because it's not so clear anymore. Get a contradiction. In one way or the other, you get a contradiction. Now, how do you do that? Well, a proof is a list of statements that are true that you derived, one statement that you derive from a previous statement using some assumptions and so on, all correct using rules of inference. So you have a whole list of statements. Now, if in that list, by accident, the statement R appears, and a bit later the statement not R appears, you're in trouble, right? Because if this is a statement of all true things, then all of a sudden something is true and at the same time false. That's a contradiction. So that's what you want to establish. You want to establish that assuming not P, the consequences of not P are such strange consequences that they imply one statement to hold, whereas it at the same time doesn't hold. Okay, that is hard to perhaps parse, so I have to do several examples. So the first is a rather easy one. The theorem says, theorem, okay, so I'm going to call it a theorem, it's not a theorem. Among 22 different dates, calendar dates in a particular year, there are at least 4 on the same day of the week. It's not so immediately obvious, right? If I give you 22 dates, let's say, for simplicity, let's take everybody's birthday, and then what I'm claiming is if there are 22 people in the class and nobody has the same birthday, which is not the probability is not so. There could very well be that 2 people have the same birthday, but let's assume that nobody has the same birthday of these 22 people. Then I'm claiming 4 of these people were born or have their birthday on the same day, weekday, same day of the week, meaning Monday, Tuesday, blah, 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 to Sunday. Okay, so proof by contradiction. So what do we have to do? Well, this whole statement here, it was P, and what we have to do is assume that the negation is true. So assume not this thing. What does that mean? Among 22 different days, there are at least 4 on the same day of the week. That means we have 22 days, but every of them are on at most 3 on each weekday. So assume not. So this means at most 3 dates. It's not 4, so it's most 3 on Monday. And of course, most of these 3 are on Monday. At most of 3 are on Tuesday. At most 3 are on Wednesday. I can't, because I don't want to have 4, right? I mean, I'm saying it's not going to happen. I'm going to assume a world in which not this 22 different birthdays, but none of them are on no more. Sorry, no 4 or more are on the same weekday. Therefore, at most 3 are on the same weekday. At most 3 on Monday. At most 3 on Wednesday. At most on Tuesday. And so let's keep going to our list. On Thursday, on Friday, on Saturday, and then finally on Sunday. That's it. Okay, but how many days I have now? Total of days. Let's try to count how many days I have now arranged in this way. Now, at most is it 3. So let's assume it's as bad or as much as it could be 3. Assume it's 3 on Monday, 3 on Tuesday, 3 on Wednesday. How many days do I have? 3 plus 3 plus 3 plus 3, 7 times. So 3 times 7 is 21. I don't have enough days. Remember, there should have been 22 days, and I won't come only up with 21 days. So that means, what is the contradiction here? If there were 20, if I assume not that there are 22 different dates, that each of which is at most on 3 of which are on the same weekday. If I assume that, then I come up with the fact that there are at most 21 dates. So there are at most 21 days, but there are 22 days, so I'm contradicting my assumption that there were 22 days. Okay, that's a proof by contradiction. And I write it as like a bolt, like an electricity bolt, like your shortcuts, whatever you call it, that's contradiction. But okay, if you don't want to make this kind of notations, you can say contradiction. And so we are done. That is strange, right? I'm contradicting it. Somehow it seems that we have veered away from the actual problem, and we got about something. We're talking now about the number of days. Okay. Okay. Here's another one, a very famous one. Theorem: radical 2 is irrational. The radical of 2 is an irrational number. Now, remind you that rational means that you're a fraction of 2 integers. Of course, the denominator cannot be 0. And irrational means you're not. Okay? So, proof by contradiction. Why, in this particular case, I really want to do contradiction? First of all, I cannot do contraposition. Why not? Because it's not an implication, right? There's no implication, so what is there to contrapose, if you want? But contradiction I can do. Why do I think even... that's another question. I'm going to explain you what proofs by contradiction is, but the next question would be, when do you use them? Well, let me give you a little insight here. The reason I'm going to use it is because to be irrational means you cannot be written as a fraction. Okay, how am I going to work with the fact that something is not a fraction? The negation of which is much easier. You can be written as a fraction. Oh, can I write down a fraction and I'm good, right? So assume not. Assume that what you're saying is not true. This means radical 2 is rational. Right? That's what I'm just saying. Now, before we go with the actual proof, let's remind us what we have to show. To show, well, to show is perhaps the wrong word. To get a contradiction. Now, the thing is, I cannot predict yet what the contradiction will be. Perhaps the contradiction is my left thumb is 5 centimeter and my left thumb is 7 centimeter. That contradicts each other. Now, of course, I don't see how my left thumb is going to ever be applied come up in this kind of proof. But I'm just saying, a priori we don't know what is going to happen here. So let's start. Okay, proof. I mean, I start of the argument. Let me put it that. Radical 2 is rational. That means radical 2 can be written as a fraction of a fraction, m and n. So m and n are integers. And of course, n is not 0. But we know we can do better. We can always reduce a fraction. So I'm going to say that this is a reduced fraction. Remember, this means that I have factored out any common factor. Right? So, for instance, 4 over 6 is not reduced because that is 2 over 3. That is reduced. Okay? Everybody remembers this, right? What reduced means. Okay. So, oh no, that's not what I want to do. Good. Okay, so at least I have something to work with. One thing I've learned is that with radicals you don't want to work with, so you square them. Okay, let's square. We square both sides. So we get now 2 is equal to m squared over n squared, right? That's what happens when you square a fraction. I don't want fractions anymore, so I'm going to cross multiply. 2n squared is equal to m squared. So this tells me that m squared is even. So m squared is even, right? Because it's a multiple of 2, right? This here tells me that m squared is even. Now, I skipped this and I now realize I perhaps shouldn't have done this, but it is in the textbook in example 8, so I'm going to leave that as an exercise for you because it's also approved by contradiction. In example 8, you show that if m squared even implies m even. So it's an if you want, try to do it for yourself here to prove it. Oh, there it's actually, the actual exercise is odd, but it's the same thing. If m squared is even, then m is even. So try to prove this by contradiction. You can also prove it by contraposition, by the way. So you can use either way. Very often, a proof of by contradiction involving an implication can also be done by contraposition. But, okay. So m squared is even. Okay, so from this now we know that m is even. Okay, I'm referring to this theorem. That's of course what mathematicians all the time do. They're not going to start proving everything from scratch, right? You're not keep reinventing the wheel. Once somebody else has proven this, you say, oh, this guy has proven this, and I'm going to use this now, and so I can conclude m is even. Okay, what does that mean? That means that m can be written as 2k for some k. Yeah, so here I should have said for some. I said it, but I didn't write it down. So for some k, m is 2k. But the only thing I can do is plug everything in. So now I have 2n squared is 2k squared, which is 4k squared. Oh, I can reduce this a little bit. From this I see that n squared is 2k squared. Right? I just divided both sides by 2. Oh, wait, but this says that n squared is even, because it's a multiple of 2. Right? This 2 here shows me that it is n squared is even. And from this theorem that somebody has proven for me, I know now that n is even. Yeah, but wait a sec. N is even, m is even, and it's a reduced fraction, which means that m and m have no common factor. That doesn't sound correct. Because to be even means you have a factor 2. And so here we have this m is even, n is even, so they both have a common factor, whereas this says they don't have a common factor. So here we see we have one statement is true and its negation is true too. That's impossible. That is the contradiction. And notice that, as I said, it was not clear immediately that we were going. So contradiction. When you say this contradiction, you should perhaps, okay, I'm now saying it in words, but if you write it down, you should say the contradiction that m is even, n is even, is with, you have to say, what is it a contradiction with? It is a contradiction with this guy that I just had circled. Okay. End of proof. Remember our first thing that we proved by contraposition, and I said this and I want to come back to this. When you do a proof by contraposition, remember we were proving here this statement. Okay, I'm trying to prove this statement here. I did that by contraposition, and very often contraposition and contradiction, you can go either way. Not always, but often you can. Well, of course, for one thing, it has to be an implication, because contraposition only applies to implication. So, for instance, there was no way that we could use a contraposition to prove this statement, because not an implication. Okay, so I'm going to go to the same theorem here. So, if, what was it, 3m squared, 3n plus 2 is odd, then n is odd. proof by contradiction. Suppose not. Now we have to think a little bit about this. So we have here an implication, right? P then Q. This is P. This is Q. What means not P then Q? Think a bit about it. When is an implication false? Well, it's false only in the following situation, that P is true but Q is false. So if I say suppose not, suppose, in other words, I cannot, not when you mean a double negation here. Suppose we don't have this implication, that means that we assume that this is true. So to get, the goal is to get a contradiction. So get contradiction from this. And you see that it's kind of possible, right? Because we have two statements, P, and another statement, it's a negative one, but okay, it's not Q. And so perhaps one statement implies one thing and the other statement implies the other thing, the negation. So, okay, let's see where we can go with this. P is true. So, P says that 3n plus 2 is odd. Okay. And what is Q? Not Q. Then says that n is even, right? Not odd. I know what this means. It means that n is 2k. Now, I also know what the top one means, but as you see, writing out what that means is not going to help me. But using this is going to help me. I'll show you. I can now plug this in 3n plus 2. So 3n plus 2 is equal to basically the same argument. If you think about it, is almost the same argument as we just did. We plug in 2k, we get 6k plus 2, but more importantly, I can factor out the 2. I get 3k plus 1, and so I see that 3n plus 2 is even. Hey, wait a sec. I just said it was odd. So in other words, I just got not P here, and I have already P. So these two together is the contradiction. And we're done. Okay, I think there are a bit more about proofs, and I want you to read a little bit about this. But for the homeworks, I'm going to concentrate on proofs by contraposition and proofs by contradiction. Especially the last one probably needs some work. So I'm going to perhaps assign a little bit more homework problems and go over them next time.